Passive fire protection is an integral component of the three components of structural fire protection and fire safety in a building. PFP attempts to contain fires or slow the spread, through use of fire-resistant walls, floors, and doors. PFP systems must comply with the associated listing and approval use and compliance in order to provide the effectiveness expected by building codes. Structural fire protection in a building, offshore facility or a ship is a system that includes active fire protection, which can include manual or automatic fire detection and fire suppression. Passive fire protection, which includes compartmentalization of the overall building through the use of fire resistance rated walls and floors. Organization into smaller fire compartments, consisting of one or more rooms or floors, prevents or slows the spread of fire from the room of fire origin to other building spaces, limiting building damage and providing more time to the building occupants for emergency evacuation or to reach an area of refuge. Fire prevention includes minimizing ignition sources, as well as educating the occupants and operators of the facility, ship or structure concerning operation and maintenance of fire-related systems for correct function, and emergency procedures including notification for fire service response and emergency evacuation. Main characteristics: the aim for fire protection systems is typically demonstrated in fire testing, the ability to maintain the item or the side to be protected at or below either 140 degrees Celsius or circa 550 degrees Celsius, which is considered the critical temperature for structural steel, above which it is in jeopardy of losing its strength, leading to collapse. This is based, in most countries, on the basic test standards for walls and floors, such as BS 476, Part 22, 1987, BSEN 1364-1, 1999 and BSEN 1364-2, 1999 or ASTM E119. Smaller components, such as fire dampers, fire doors, etc., follow suits in the main intentions of the basic standard for walls and floors. Fire testing involves live fire exposures upwards of 1100 degrees Celsius, depending on the fire resistance rating and duration one is after. More items than just fire exposures are typically required to be tested to ensure the survivability of the system under realistic conditions. To accomplish these aims, many different types of materials are employed in the design and construction of systems. For instance, common endothermic building materials include calcium silicate board, concrete and gypsum wallboard. During fire testing of concrete floor slabs, water can be seen to boil out of a slab. Gypsum wallboard typically loses all its strength during a fire. The use of endothermic materials is established and proven to be sound engineering practice. The chemically bound water inside these materials sublimes. During this process, the unexposed side cannot exceed the boiling point of water. Once the hydrates are spent, the temperature on the unexposed side of an endothermic fire barrier tends to rise rapidly. Too much water can be a problem, however. Concrete slabs that are too wet will literally explode in a fire, which is why test laboratories insist on measuring water content of concrete and mortar in fire test specimens, before running any fire tests. PFP measures can also include intrumescence and ablative materials. The point is, however, that whatever the nature of the materials, they on their own bear no rating. They must be organized into systems, which bear a rating when installed in accordance with certification listings or established catalogues, such as DIN 4102 Part 4 or the Canadian National Building Code. Passive fire protection measures are intended to contain a fire in the fire compartment of origin, thus limiting the spread of fire and smoke for a limited period of time, as determined the local building code and fire code. Passive fire protection measures, such as fire stops, fire walls, and fire doors, are tested to determine the fire resistance rating of the final assembly, usually expressed in terms of hours of fire resistance. A certification listing provides the limitations of the rating. Contrary to active fire protection measures, passive fire protection means do not typically require electric or electronic activation or a degree of motion. Exceptions to that particular rule of thumb are fire dampers and fire door closers, which must move, open and shut in order to work. as well as all intumescent products, which swell, thus move, in order to function. As the name suggests, passive fire protection remains inactive in the coating system until a fire occurs. There are mainly two types of PFP, intumescent fire protection and vermiculite fire protection. In vermiculite fire protection, the structural steel members are covered with vermiculite materials, mostly a very thick layer. This is a cheaper option as compared to an intumescent one, but is very crude and aesthetically unpleasant. Moreover, if the environment is corrosive in nature, then the vermiculite option is not advisable, as there is the possibility of water seeping into it, and there it is difficult to monitor for corrosion. Intumescent fireproofing is a layer of paint which is applied along with the coating system on the structural steel members. The thickness of this intumescent coating is dependent on the steel section used. For calculation of DFT, a factor called horsepower per hour, referred to as section factor, and expressed in MAR1, is used. Intumescent coatings are applied as an intermediate coat in a coating system. Because of the relatively low thickness of this intumescent coating, nice finish, and anti-corrosive nature, intumescent coatings are preferred on the basis of aesthetics and performance. It should be noted that in the eventuality of a fire, the steel structure will eventually collapse once the steel attains the critical core temperature. The PFP system will only delay this by creating a layer of char between the steel and fire. Depending upon the requirement, PFP systems can provide fire ratings in excess of 120 minutes. PFP systems are highly recommended in infrastructure projects as they can save lives and property. PFP in a building can be described as a group of systems within systems. An installed fire stop, for instance, is a system that is based upon a product certification listing. It forms part of a fire resistance rated wall or floor, and this wall or floor forms part of a fire compartment which forms an integral part of the overall fire safety plan of the building. The building itself, as a whole, can also be seen as a system. Examples: fire resistance rated walls. Firewalls not only have a rating, they are also designed to subdivide buildings such that if collapse occurs on one side, this will not affect the other side. They can also be used to eliminate the need for sprinklers, as a trade-off. Fire-resistant glass using multi-layer intumescent technology or wire mesh embedded within the glass may be used in the fabrication of fire resistance rated windows in walls or fire doors. Fire resistance rated floors, occupancy separations. Closures. Sometimes fire stops are treated in building codes identically to closures. Canada rates closures, where, for instance, a 2-hour closure is acceptable for use in a 3-hour fire separation, so long as the fire separation is not an occupancy separation or firewall. The lowered rating is then referred to as a fire protection rating, both for fire stops, unless they contain plastic pipes, and regular closures, fire stops. Grease ducts. In North America, grease ducts are made of minimum 16-gauge sheet metal, all welded, and certified openings for cleaning, whereby the ducting is either inherently manufactured to have a specific fire resistance rating, or it is ordinary 16-gauge ductwork with an exterior layer of purpose-made and certified fireproofing. Either way, North American grease ducts must comply with NFPA 96 requirements. Cable coating. Spray fireproofing vessels, vessel skirts, bulkheads or decks below either 140 degrees Celsius for electrical items or circa 500 degrees Celsius for structural steel elements to maintain operability of the item to be protected. Fireproofing cladding materials for such cladding include perlite, vermiculite, calcium silicate, gypsum, intumescent epoxy, durasteel, microtherm, enclosures, or the provision of circuit integrity measures to keep electrical cables operational during an accidental fire. Regulations. The most important goal of PFP is identical to that of all fire protection, life safety. This is mainly accomplished by maintaining structural integrity for a time during the fire, and limiting the spread of fire and the effects thereof. Property protection and continuity of operations are usually secondary objectives in codes. Exceptions include nuclear facilities and marine applications, as evacuation may be more complex or impossible. Nuclear facilities, both buildings and ships, must also ensure the nuclear reactor does not experience a nuclear meltdown. In this case, fixing the reactor may be more important than evacuation for key safety personnel. Examples of testing that underlies certification listing: Europe BSEN 1364, Netherlands, NEN 6068, Germany, DIN 4102, United Kingdom, BS 476, Canada, ULCS 101, United States, ASTM E119. Each of these test procedures have very similar fire endurance regimes and heat transfer limitations. Differences include the hose stream tests, which are unique to Canada and the United States, whereas Germany includes a very rigorous impact test during the fire for firewalls. Germany is unique in including heat-induced expansion and collapse of ferrous cable trays into account for fire stops, resulting in the favoring of fire stop mortars, which tend to hold the penetrating cable tray in place, whereas soft seals, typically made of rockwool and elastomeric toppings, have been demonstrated in testing by Otto Graf Institute to be torn open and rendered inoperable when the cable tray expands, pushes in and then collapses. Spin-offs from these basic tests cover closures, fire stops and more. Furnace operations, thermocoupling and reporting requirements remain uniform within each country. In exterior applications for the offshore and the petroleum sectors, the fire endurance testing uses a higher temperature and faster heat rise, whereas in interior applications, such as office buildings, factories and residential, the fire endurance is based upon experiences gained from burning wood. The interior fire time temperature curve is referred to as ETK, or the building elements curve, whereas the high temperature variety is called the hydrocarbon curve as it is based on burning oil and gas products, which burn hotter and faster. The most severe, and most rarely used, of all fire exposure tests is the British jet fire test, which has been used to some extent in the UK and Norway but is not typically found in common regulations. Typically, during the construction of buildings, fire protective systems must conform to the requirements of building code that was in effect on the day that the building permit was applied for. Enforcement for compliance with building codes is typically the responsibility of municipal building departments. Once construction is complete, the building must maintain its design basis by remaining in compliance with the current fire code, which is enforced by the fire prevention officers of the municipal fire department. An up-to-date fire protection plan, containing a complete inventory and maintenance details of all fire protection components, including fire stops, fireproofing, fire sprinklers, fire detectors, fire alarm systems, fire extinguishers, etc. are typical requirements for demonstration of compliance with applicable laws and regulations. In order to know whether or not one's building is in compliance with fire safety regulations, it is helpful to know what systems one has in place and what their installation and maintenance are based upon. Changes to fire protection systems or items affecting the structural or fire integrity or use of a building is subject to regulatory scrutiny. A contemplated change to a facility requires a building permit, or, if the change is very minor, a review by the local fire prevention officer. Such reviews by the authority having jurisdiction also help to prevent potential problems that may not be apparent to a building owner or contractors. Large and very common deficiencies in existing buildings include the disabling of fire door closers through propping the doors open and running rugs through them and perforating fire resistance rated walls and floors without proper fire stopping. Old versus new. Generally, one differentiates between old and new barrier systems. Old systems have been tested and verified by governmental authorities including DIPT, the British Standards Institute and the National Research Council's Institute for Research in Construction. These organizations each publishing codes and standards, wall and floor assembly details that can be used with generic, standardized components, to achieve quantified fire resistance ratings. Architects routinely refer to these details in drawings to enable contractors to build passive fire protection barriers of certain ratings. The old systems are sometimes added to, through testing performed in governmental laboratories such as those maintained by Canada's Institute for Research in Construction, which then publishes the results in Canada's National Building Code. Germany and the UK, by comparison, published their old systems in respective standards, DIN 4102 Part 4 and BS 476. New systems are typically based on certification listings, whereby the installed configuration must comply with the tolerances set out in the certification listing. The United Kingdom is an exception to this, whereby certification, although not testing, is optional. Countries with optional certification, fire tests in the UK are reported in the form of test results, but contrary to North America and Germany, building authorities do not require written proof that the materials that have been installed on site are actually identical to the materials and products that were used in the test. The test report is also often interpreted by engineers, as the test results are not communicated in the form of uniformly structured listings. In the UK, and other countries which do not require certification, the proof that the manufacturer has not substituted other materials apart from those used in the original testing is based on trust in the ethics or the culpability of the manufacturer. While in North America and in Germany, product certification is the key to the success and legal defensibility of passive fire protection barriers, alternate quality control certifications of specific installation companies and their work is available, though not a legislative or regulatory requirement. Still, the question of how one can be sure, apart from faith in the vendor, that what was tested is identical to that which has been bought and installed is a matter of personal judgment. The most highly publicized example of PFP systems which were not subject of certification and were declared inoperable by the authority having jurisdiction is the Thermolag scandal, which was brought to light by whistleblower Gerald W. Brown, who notified the Nuclear Regulatory Commission of the inadequacy of fire testing for circuit integrity measures in use in licensed nuclear power plants. This led to a congressional inquiry, significant press coverage and a large amount of remedial work on the part of the industry to mitigate the problem. There is no known case of similar instance for PFP systems which were under the follow-up regime of organizations holding national accreditation for product certification, such as DIEPT or Underwriters Laboratories. See also, pressurization ductwork, smoke exhaust ductwork, flammability, mortar, fire stop pillow, drywall, fire protection engineering, fire resistance rating. References. External links, Association for Specialist Fire Protection, Burning Down the House, European Association for Passive Fire Protection, AIA-approved fire-rated glass and glazing course, Gar 1/4 Tagesgemeinschaft Brandschutzimmagebau, Passive Fire Protection Federation, PFPF definition of passive fire protection. International Firestop Council, Firestop Contractors International Association, videos showing flammability of cables based on jacket rating, fire protection safety procedures, treatise on active and passive fire protection from UK Government, UK Furniture and Furnishings Regulations 1988/1989, 1993 and 2010, Passive Fire Limited, an independent advisory service for all.